Hello, we invite you to another session on R language in our series, the R language primer. In this class, we are going to talk about operators in the R language. Operators are symbols which the computer recognizes, and each symbol means a specific thing to the compiler. They can be either arithmetic operations or logical manipulation or a whole host of other things as we'll go ahead now. In the first, we are trying to summarize these operators into 5 groups. The arithmetic operators like addition, subtraction, the assignment operators which assign a value, a numeric value or a string value or a character value to a variable, logical operators which return the values true or false, relational operators which try to compare two values and show us which is the greater of the two values or lesser of the two values and so on. And we have a few miscellaneous operators which we will go ahead. Let's look at the operators, the arithmetic operators. The first one is an add, a plus sign, which adds two vectors. We have minus sign, which subtracts the second vector from the first. The asterisk is a multiply operation. Slash is a division operation. The two percentage symbols, percent symbols close together, return the remainder when the first vector is divided by the second. It's similar to the modulus which you use in maths, the remainder part. The %/% is the whole number portion when the first vector is divided by the second. So when you divide, let's say we divide 5 by 2, we'll get 2 as the whole number portion. The raised to the power of symbol, the exponential notation symbol, is to raise a given number, the first vector, to the power of the second vector. We'll quickly run through some examples. All of these have been run in the R console or the R studio, whichever is convenient to you. The lab here has tested them on both. And the outputs have also been pasted. We are not running the examples and recording the R console, but you can do it in your own time, at your own convenience, and send us a mail if you have any difficulties. The first example, we have got two vectors P and Q where we are assigning the values, and then we add these vectors. So you can see it's added 3 plus 6, which is 9, 6.5 plus 5, which is 11.5, and 10 plus 7, which is 17. This is the output pasted from the R studio and the R console. The same example we are now continuing. We now have the subtract operator where each value from the second vector is subtracted from the first vector. So we have a -3, a 1.5 and so on. The output has been pasted in the screen here. Then we have the multiplication operator where each vector is multiplied, like 3 into 6, 6.5 into 5.7 and 10 into 7. The output is pasted here and you could see the same answers. The division operator, again, which is the same thing, the first vector being divided by the second. So we had a 0.5, a 1.3 and a 1.42, 8571, etc. Output of the division is also pasted here for your convenience. If you have any difficulty, please mail us. Then we have the remainder operator where we have the two % symbols close together. We have two vectors P and Q, and then we are dividing for the remainder part P % Q. We get the answer is 3 by 6. Whole number is not there, and we'll get 3 as the remainder. 6.5 by 5, we'll get this 1.5 as the remainder. 10 by 7, we'll get 3 as the remainder. Output from the R console, the R studio is available to you. Then we have the %/% operator which returns the whole number part. So 3 by 6 is only a decimal portion, there is no whole number part. So we see a 0. 6.5 by 5.7 it goes in once, so we get 1 as the answer. And 10 by 7, 7 goes into 10 once, so we get 1 as the answer. You can see the output on the screen, which has been run in the R Studio or the R console. We go to the exponential operator where we are going to raise the first value to the index given by the second value to the power of. So in the first example it will be 3 power 6, second example it will be 6.5 power 5, in the third example it will be 10 power 7. You can see the output from the R environment. Next we go to a set of operators which are called logical operators. These are applicable to vectors of type logical, numeric or complex. To understand this easily, think of a logical operator as having only two values or two states. It's either true or it is false. A 0 will take the value false, and a non-zero value, which is 1 or above, will take the value true. So that is why numeric or complex can also be taken as logical in the right context, of course. If the numeric or complex value is 0, it's false. If it is 1 or above, it is true. Now we call these values true and false as boolean values. So the operators here are a single ampersand, which is an element-wise comparison. If both are true, the output is true. The vertical line is the OR operator, OR, and here if any one is true, the result is true. We have the exclamation mark, which is called the NOT operator, NOT, and this takes whatever is the value given to it and returns the other state. If the input state was true, it will return false. If the input state was false, it will return true. The double ampersand compares the first element of both the vectors and returns true only if both elements are true. The OR also is very similar, except that it returns true if only one of them is true. I just remember the single ampersand and the single vertical sign work for each element in the vector, whereas the double ampersand and the double vertical lines will work only for the first element in the vector. So here we have an example of vectors being P and Q, and we are printing P ampersand Q. 7 and 3 are true, so the outcome is true. False and true, the outcome is false, because they are talking about an AND operator. 1 and 1, both are true, the outcome is true. Then the last two complex values, 6 plus 3i and 6 plus 3i are both above 1, so the resulting value is true. You can see the output from the R environment. Now we have the vertical symbol, which is the OR operator. The first values are compared, and then we get the answers as true, true, false, true. And here we have the output. And then we go to the NOT operator, which is the negative, the reverse of whatever the state is. So 7 is true, so it becomes false. 0 is false, so it becomes true. False is false, so it becomes true. 6.2i is true, so it becomes false. You can see the output from the R environment. Then we go to the second set of logical operators, which are the two ampersands. We have the two ampersands will consider only the first vector in those, first value in those two vectors. So only the 7 and 3 are compared, and the output is true. The output from the R console is shown on your screen. And you take the OR operator, it again compares the first two values from first value from each of the two vectors. So the output is 0, 0, which becomes false. Output from the R environment is shown now. Then we have a next set of operators which compare values, like whether they are greater, less, or equal. Now, these are called the relational operators. The first value is compared with the second value, and a boolean value is returned as the outcome. We have the single greater than, which returns true if each element of the vector is greater than the corresponding element of the second vector. We have the less than, which is the opposite of the true. Here we have each element is less than the corresponding element, it will return true. The double equal sign is for equality. The less than equal and the greater than equal are used when we want to include the value used in the comparison statement. Basically the limits and the boundaries. And the exclamation mark and the equal returns true if it is not equal to, which is two values being different from each other, will return a true. Now we look at a series of examples for the relational operators. We are looking at the greater than, the less than, the double equal, which is equality, the less than equal and greater than equal, and the not equal. So given our values in P and Q, each of those operations will be carried out on each element, the first element compared to the second element, and we have the output shown in the bottom of this slide. You also have the output coming from the R environment. The miscellaneous operators are, we have a colon which creates a series of sequential numbers, like let's say 1 to 5 or say 6 to 10. So if it's 1 to 5, we would say 1 colon 5. We also have another operator which is the percent in and the percent to identify whether an element belongs to a vector. Basically, we are trying to see whether the value we are having is actually found in the group of values within which we are looking. We also have a percent, ampersand percent, to multiply a matrix with its transpose. So we're coming to the colon operator. We have the statement P and we are assigning the value 1 is to 5. So that should generate the numbers 1, 2, 3, 4 and 5 as shown in the output. It's also shown in the R environment. The next example is a percent in percent operator where we have three values, 4, 6 and 1.5. And we are trying to print these values now. We are asking the question whether P is found in any of the values R. Since R is going to take the values 1 to 5, 1, 2, 3, 4, 5, the first print will return the value true. The second one, we are talking about Q being in R. There is 6, R is only 1.5, so it will return the value false. The output from the R environment is given. Now, our next example, we have the matrix multiplication. Our matrix has the numbers 1, 2, 3, 4, 5, 6. It has 2 rows and 3 columns. And by row is true, which means we'll get 1, 2, 3 in the first row, 4, 5, 6 in the second row. We are multiplying this matrix with the transpose of the same matrix. You can see the answers, and we also show you the output from the R environment. We'll also explain what is meant by the transpose of a matrix. So here we have the matrix 1, 2, 3, 4, 5, 6 as it would have happened in the code in the slide shown here. And we now take the columns as rows, which is the transposed matrix. So instead of the 1, 2, 3 being the row, we'll take 1, 2, 3 as the column, 4, 5, 6 as the second column. So we have the original matrix, we have the transpose of the matrix. The command in our programs asked us to multiply these two matrices, the first one and the second one. To multiply two matrices, we have to take the first element in the first row and multiply it by the first element in the first column. Take the second element in the first row and multiply it by the second element in the first column. Take the third element in the first row, multiply it by the third element in the third column. So doing that, we have 1 into 1 plus 2 into 2 plus 3 into 3. Then we repeat it again. We now have 4 into 1, which is, now we have now taken the second row and multiplying it by the first column. We have 4 into 1, 5 into 2, 6 into 3. 6 is the third element in the second row. 3 is the third element in the first column of the transpose matrix. So simplifying these two, we'll get 1 plus 4 plus 9 and we'll get 4 plus 10 plus 18. Now let's go to the second column of the transpose matrix. Take the first row of the original matrix, which is 1, 2, 3. The transpose matrix columns are 4, 5, 6. We'll have 1 into 4 plus 2 into 5 plus 3 into 6. And again we'll have, take the second row of the original matrix, 4 into 4 plus 5 into 5 plus 6 into 6. Simplifying it, we'll get 4, 10 and 18, 16, 25 and 36. Now once we have all these numbers, we have to arrange them as a matrix. If we take the 1 plus 4 plus 9, we get 14. 4 plus 10 plus 18, we get 32. Then 4 plus 10 plus 18, again we get 32. 16, 25 and 36, we add them together, we get 77. So when we go back to our example here, we multiplied a given matrix by its own transpose, and you can check the answers. Change the values of the numbers and you can check out the transpose of each of these. We thank you for having taken part in this next video. You have done a great work. You have completed another chapter from our Learn Data Science series, the R Primer. You can always revisit this video and any of our earlier videos. Please contact us if you need any help at datumscientia@gmail.com. Trust yourself, you know more than you think you do. Till our next lesson, it's goodbye from all of us.